Hi, my name is Alan, and today I'm going to be going over the code behind a simple neural network that can classify the digits 0 through 9 using the MNIST dataset. And so for the purposes of this video, I know that when I first started getting into machine learning, even though I knew the concepts, I had a really hard time of visualizing how the code would work. And so my learning was kind of obstructed by that. And so what I hope to do with this video is to provide you some clarification and to show you how simple the code really is, and hopefully encourage you along your machine learning journey. So before we actually jump into the code, I just want to preface by saying, one, I'm assuming that you already have some knowledge in neural networks, so I'm not going to explain that in this video. Two, don't worry about it if you don't completely understand how all of the code functions. This video is just meant to give you a very high-level overview of how easy it really is to create a simple neural network and hopefully prevent you from being intimidated like I was when I first saw the code. And so initially we want to import all the necessary modules and libraries. Then we want to define a transform to normalize the data. We're first going to convert the data to a tensor, which is essentially just a NumPy array, except it can be run on the CPU or GPU. Then we're going to normalize the data to make it easier for the model to run. And here we want to download and load the training data. We're going to get the MNIST data set. We're going to get the training and test data here, right? And so now defining our model, now that we have all the data, the necessary data, we're going to call it class classifier. And here in the init method, we're going to define all of our layers. And so the way Pytorch works is that it has a really convenient module called nn.linear. And this creates a layer with a certain number of inputs and outputs, right? So in this case, we'll have 784 inputs initialized with random weights and biases, and 256 outputs. And so it will actually do the calculation for you, doing the inputs times the weights plus the biases for you. So that's really convenient about Pytorch. And so we're just going to create two hidden layers, and then finally the output layer, we're going to return out 10. And the reason we return 10 is because we're classifying the digits 0 to 9, and so it's expected that there should be 10 different outcomes. And so the images we're passing in is actually going to be in the form of a 28 by 28 image. And so we're going to want to flatten that to 784, right? And so basically this flattens the image into that 784 columns, and that's why we have this here. And here we actually pass in the data to the first layer, and then we call the ReLU activation function on the output. Remember, ReLU activation function is just to speed up the process for the model. And we're going to do that for the next 3 layers. But finally, on the 4th layer, where we want the probabilities, right? We want the probabilities of what the image is, of what digit the image is. And so we're going to call the log softmax function, which is just it will give us the log of the probabilities. Here we're actually going to train our model. So our model, we're going to define it as classifier, which we just created here. And the criterion we're going to use is negative log likelihood loss. This is just one loss function we're using. And in this case, we're using this because it takes in log probabilities and as one of its parameters. And here, the optimizer, we're going to use the atom optimizer. This is just going to update the weights for us, the weights and the biases for us later, or the parameters of the model. And it's going to update them at a learning rate of 0.003. So we're going to run this model for 10 epochs. And for each of the images and corresponding labels in the train loader, we're going to pass in each image right into the model, which will give us the log probabilities, right? That's what we define here with the log softmax function. And then, as we stated earlier, we're using the negative log likelihood loss function, which is our criterion, and that takes in the log probabilities and the labels, and it returns a loss. It returns a loss value, which will tell us how far off we are from the correct label, right? How far off the probabilities are. And then next, from that loss, we're going to calculate the gradient of how big of a step we should take, and optimizer.step will actually update our parameters, our weights and biases. It will update that. And finally, optimizer.zeroGrad, we're going to have to clear out our gradients after we're done, or else it's just going to stay behind and that's just going to be messy. And so here, we're just going to append in the loss to the running loss. And here we're going to actually print out our epochs and our training loss, right? So on the first one, you can see that our training loss was fairly high with 0.34. But then as we kept training, it went lower and lower until it became 0.078, which is fairly low, right? And so now we can actually test out our model on a image. So you can see here, don't worry about this for now, but you can see here how we have the image 9, and the probability that this is 9 is very high, right? In fact, it's everything. And now for 2, see, it will now go to a 2. 0, it will go 0. 1, it will go 1. 6, it will go 6, right? And so you can see our model is pretty accurate, right? And so, yeah, I hope this video helped you out.